Today we are going to have this third session of this unit number 5. Myself, Professor Dr. Sandeep Ohar. Today we will discuss something about the semiconductors. I think in previous session we have discussed something about the resistivity materials, low resistivity materials as well as high resistivity materials. We have also discussed the typical applications or typical examples of the low resistivity materials as well as high resistivity materials that we have discussed in the previous class. Today we are going to discuss something about the semiconducting materials, because nowadays this industry is coming like a huge opportunities for the engineers, those who are working in the domain of semiconductors. Our government, central government is investing a lot amount in this particular industry to develop the semiconductors inside India only, because these are having a huge applications. Basically, if you see semiconductor, it comes in between the insulator and the conductor. As the name itself indicates, semi means partial conduction. Semi means partial. So whatever the materials which are available or whatever these semiconductor materials are basically lie in between the insulating materials and the. Can you see what is semiconductor, or if you want to ask me what exactly the meaning of semiconductor, that you can see that these are the materials which are having conductivity in between insulators and the insulators and the conductors. These are a compound of kind of gallium arsenide, okay, kind of impure extrinsic type of semiconductor. This is called as extrinsic, means in which there is impurity is there in that particular semiconductor. Those are called as extrinsic. And intrinsic semiconductors are there. That means they are having a pure element or acting as a semiconductor. So gallium arsenide is a kind of extrinsic, and we can also have some germanium or silicon. These are the semiconductors which can be used as a pure semiconductors. If you say gallium arsenide, this is germanium and silicon are some of the most commonly used semiconductors nowadays. Silicon is used in electronic circuits. Basically, these silicon semiconductors are used in electronic circuit fabrication, and gallium arsenide are used in solar cells or some laser diodes. So these are the common or in general applications of this particular main type of semiconductors, like germanium, like gallium arsenide as well as germanium or silicon. Again, you can say that semiconductor can conduct electricity under preferred or preferable condition. That means if you want to ask that semiconducting material to conduct the electricity at certain conditions, that means at this particular temperature and at this particular pressure. Likewise, you can preferably ask that semiconductor to conduct the electricity through them, and that is the unique property of the semiconductors. That's why they are having huge applications, and that's why our government is investing a lot of money in that particular semiconductor industry. If I want that semiconductor material should conduct the electricity at 20 degrees Celsius or at 40 degrees Celsius, I can do with the help of that semiconducting material. So that's why the word here mentioned preferable condition. That means whatever the condition I need, whatever the conditions are there for conducting the current, that condition, in that particular condition, semiconductors can conduct the electricity. So this unique property makes them excellent material to conduct the electricity at a controlled manner as required. Why I am giving more stress on this preferable condition, because I don't know at what condition I have to conduct the electricity. If I go in North India, nowadays there is kind of huge cold is there. So in that case, I want to conduct the electricity. Now here in Maharashtra or something, huge temperature is there. Yesterday it was I think more than 42 degrees Celsius in the night. So that in this kind of condition, if I want to conduct the electricity from one place to another place, semiconductors are the devices which can be used for this preferable conditions. What are the general properties of the semiconductors? That is discussed in the next slide. You can see that at 0 Kelvin they are acting as an insulator. That means at what degree Celsius they are acting as a insulators? 237. 0 Kelvin means how much degree Celsius? Minus or plus? Huh? 273. प्लस कैसे हो सकता है भाई? जल जाओगे इधर, बॉयल हो जाओगे. Okay, so at 0 degree Kelvin, semiconductors are acting as insulators, and as temperature increases, on increase in the temperature, they can be acting as a conductor. That's why in the previous slide we have used the word preferable conditions or controlled conditions. Okay. Due to their exceptional electrical properties, this can be modified by doping to make semiconductor device suitable for energy conversion, may be suitable for switches, and may be suitable for amplifiers. Okay. We can have some doping, means mixing. We can mix pure semiconductor with another impurity which will work for me as a conductor of electricity. Okay, so that kind of thing, that kind of doping I can do, that kind of doping with the other elements or other semiconducting material I can do, so that whatever the resulting material I will get, that will be a good material as far as this semiconducting power or semiconducting property is concerned. They are having very less power losses while flowing the current from one place to another place. Whatever the power losses are there, that power losses are also on the minimal level. They are smaller in size and possess less weight, and that's the beauty of these semiconductors. Even though they are smaller in size and also they are less weight, that's why they are used more. They are more used in electronic industry as well. Okay. Resistivity is higher than the conductor but lesser than the insulator. Resistivity is higher than the conductor. I hope you guys are getting. Resistivity is higher than the conductor. Conductor का resistivity कितना है? Maybe 0. That's why its name is conductor, ना? So इसका semiconductor का resistivity will be more than the conductors. That means it will have some sort of resistivity. It will have some sort of resistivity, and it is lesser than the insulators. It is lesser than the insulators. समझ में आया? Resistivity of the semiconductors. It is more than the conductor. Are you convinced? Conductor means, for example, if full conducting material is there, that means there is a zero resistivity. Semi-conducting, that means there is a resistivity in that particular material, which will be more than the conducting material. Convinced? Insulators, full resistivity. Insulator means they will not allow the flow of current, and semiconducting will allow some flow of current. That's why they have it is written here that they have resistivity is higher than the conductor, but it is lesser than the insulating material. Insulating material से ज़्यादा रहेगा तो वो actually खुद insulator करके काम करेगा, isn't it? So don't be confused here. Resistance of semiconductor material decreases with increase in temperature. That's why here at 0 degree Kelvin they are acting as a pure insulator, but as your temperature increases they are acting as a semi-conducting device. We are not saying that they are acting as a pure conducting device. No, that's why the name is semi. Semi means partial. Partial conduction is there. That's why the resistance of the semiconducting material will decrease as the temperature will increase. They are highly portable due to their small size. Highly portable due to their size is small, as we have here also seen. They are smaller in size and also they are lighter in weight. That's why they are having more applications. Wide range of applications is there for these semiconducting materials. These are again shock proof. You don't have any kind of shocks during the transfer of current. Longer lifespan and noise free while operating. So these are the properties of the semiconductors. What are the different properties of the semiconductors? List out the different properties of the semiconductors. If you see the types or classification of the semiconductors, They are basically classified into intrinsic, that means they are pure semiconductors like silicon, germanium, okay, and they are extrinsic, they are impure semiconductors, and again extrinsic semiconductors are classified into two types, that is p-type and n-type, depending upon the doping done or depending upon the mixing of that particular one. So basically semiconductors of two types, intrinsic, that means they are pure semiconductors like silicon and germanium, and the impure or gallium arsenide kind of thing, that is nothing but the extrinsic semiconductors in which they are impure semiconductors, and again they are classified into two, p-type and n-type. So first of all we will see what is what is intrinsic. Basically it is pure. Here you can see that silicon semiconductor material is shown over here. There are 5 atoms of silicon. Every is having the 4 electrons in the outside area. So intrinsic semiconductors, that is crystalline structure of intrinsic semiconductor. Here you can see that does not contain any impure atom, contains only one type of atom, that is called as intrinsic. Here you can see that everywhere only one silicon atom is there. Only one silicon atom is there in this particular one. There is no another atom, that means there is no other impurity. Then electron, when an electron is free from atom of an intrinsic material, it breaks a covalent bond and leaves behind a vacancy, that is called as hole. That means from here, for example, from this particular bond, this is the covalent bond between the two silicon atoms. One electron will come out by creating the hole or vacancy at that particular position. And this hole or vacancy is going to be helpful when we are talking about the extrinsic type of semiconductors, that means impurity. That means this hole may be replaced by another atom so that it will become impure kind of p-type or n-type of semiconductor. So these are the covalent bonds, okay, and if this electron comes out of its regular site, okay, then it is going to create a hole or it is going to create a vacancy, and that is called as hole. Free electron and the hole form an electron hole pair. So if one electron is coming out from this place, that means hole is going to be created. So this electron and this hole, that is nothing but electron hole pair. Higher the temperature, greater the number of free electrons and holes. That's what. And these electrons also, in case of pure semiconductors, who is responsible for the transfer of transfer of current from one place to other place? These free electrons, na? How the electricity is getting conducted through the pure type of semiconductors. So when we are increasing the temperature of that particular semiconductor, these covalent bonds may be broken and this electron will come out and making number of electron hole pairs at that particular point or at that particular temperature. By that way current can be carried out from one place to another place. So when a voltage is applied to an intrinsic material, it acts as a conductor. Now who is acting as a conductor? Why? Because these free electrons are there. Free electrons are there, they are carrying the current. Free electrons are carrying the current, and that's why when we are applying the voltage to that particular semiconductor, it will acting as a conductor of electricity. I hope you guys have understood this one. Explain pure type of semiconductor with suitable diagram. So this diagram and this explanation is expected in the answer. And the next one is now extrinsic. So you can here see that, quite obvious, the atoms which are present in the semiconductor, there will be more than one. There is no, nothing is like that, there is only one atom. So you can see that lead is there and silicon is there. So, and this extra electron is also present, because you can see here, silicon in the previous we have seen that the 4 valency, this is valency, number of free electrons in the outer cell, that term is called as valency. So in the silicon there are 4 valence electrons. In the lead you can see that there are more than 4 electrons. So that's why one electron is coming out as an impurity. as an impurity, and that electron contributes for the free electron. So how for conduction of the electricity we need free electrons. This is the basic concept behind this. For conduction of electricity through the conducting material we need free electrons. So here in impure you can see that in the silicon and lead example, silicon lead semiconductor, you can see that one free electron is there which will be contributing for the conduction of electricity. Same another example is there, silicon and boron is there. In the silicon and boron you can see that there one electron is missing from the outer cell, and that missing electron is creating a hole, and that hole can be considered as a acceptor impurity which creates the hole. That means the material or the atom who is having the free electron may combine here and it will complete the hole, so that's why the conduction of electricity may happen. So another example here shown, silicon and aluminum. Again you can see that there is one hole is present in this particular covalent bond. So basically what is expected, or what is the principle behind conduction of electricity in the semiconducting materials, that there is a presence of electron, free electron, or there is a presence of hole. These two things are contributing for the conduction of electricity in case of semiconductor. When we apply the voltage to that particular semiconducting material, current may flow due to the movement of these electrons which are having some charge. Also current may flow due to the movement of these holes. So these two things are very much important, that is free electron and the hole for the conduction of electricity in terms of semiconducting materials. I hope you have understood this one. So we'll see what is written in that extrinsic. Pure silicon or germanium exhibits characteristics closer to that of insulator. That means conduction of electricity through the pure semiconducting materials is kind of a difficult thing. They are actually acting as a pure insulating materials, because making that electron free from the regular side and creating the hole, it is again a difficult task or hard task, and that's why pure silicon and germanium, these are closer to the insulators than the semiconductor. In order to make them material conducting, small quantity of impurity must be added to it. That's why here, as the name itself indicates that it is an impurity, so as far as logic is concerned, we have to remove that impurity because it is impurity. But as we have discussed in materials as well, when we are talking about the pure iron, there is 100% Fe in that particular material. It is soft and malleable or ductile if you compare the properties. But when I add only 0.1% of carbon to that 100% iron, that means 99.9% Fe is there and only 0.1% carbon is there, hardness increases drastically. So in that case, we can say that, or normal person can say that, not technical person may say that, अरे ये कार्बन तो impurity है उसमें, 100% pure iron था, क्यों impurity add कर रहे हो? But he don't know that due to the addition of that impurity, my properties are improving. So that's why property, if you want to have the properties, we have to add something to that so that it will improve the properties. The similar thing is again going to be applicable for semiconducting materials. Pure semiconducting material like silicon and germanium, they are acting as insulators, as good as insulators, not exactly insulators, but they are acting as good as insulators. But when we add some another impurity to them, they are acting as a semiconducting material. They are acting as a conducting material. So to improve the property of conduction of electricity of this pure semiconducting material, we are introducing the impurity into that, and that impurity is responsible for the conduction of electricity through that pure semiconducting material. Addition of impurity makes pure germanium silicon a conductor. The process of adding impurity is called as doping. In case of steel, we have called it as alloying. We have added carbon, we have called it as alloying. In case of semiconductor, it is called as doping. That means mixing again. When a pentavalent group provides an extra electron, here you can, in the lead there might be 5 electrons in the outer cell. That's why it is called as pentavalent. That means 5 free electrons are there in the outer cell of lead. Provides extra electron to the semiconductor material. The atom of the material which donates the extra electron is called as donor atom. this case, who is donor? Lead is the donor. Lead is the donor. When the trivalent group is added, trivalent means 3 electrons are free in the outer cell, like a boron case. There are 3 electrons in the outer case of boron, so it is accepting the electron. It is accepting the electron, such as silicon. One covalent bond is broken, that is, hole is going to be created. So that hole is going to be created. That means there is a provision, there is a chance to add one extra electron from pentavalent material. Okay. So when trivalent group is added to intrinsic materials such as silicon, boron is added to the silicon. Example is also shown over here. One covalent bond is going to be broken. Here one covalent bond is going to be broken and hole is going to be created. An electron from an adjacent atom can fill the hole, which is now moved to another atom. Okay, so this hole can be filled by another electron from the another atom, not from the same one. Okay, so the doping atom has now one surplus negative charge and has become negative ion. Hole is the absence of electron and hence it is a positive charge. So don't be confused here. Electron is always negative charge. Electron is always having negative charge. So extra electron means there is a negative charge. Hole means there is a positive charge. Okay. So a hole is the absence of electron and hence carries the positive charge. The doping element is an accepted since it takes or accepts the electron. So this boron is going to accept the extra electron from the adjacent silicon atom. That's why this is also called as acceptor. This is also called as acceptor in which there is hole. So the material in which there is hole in the outer cell, that particular material can be considered as an acceptor. The material in which there is an extra electron present for donation, that particular is called as donor. Okay? Understood? Am I going good, guys? Huh? So is this clear? So again, explain extrinsic semiconductor with suitable diagram. Suitable diagram as well as suitable example. Then the next, again extrinsics are classified into 2 categories, that is p-type and n-type. So when a pentavalent impurity is added to an intrinsic material such as silicon, so here you can see that phosphorus is there. By mistake वो P चाहिए यहाँ पे. Okay. So phosphorus 5 valence electrons. You can see that the 5 electrons are there in the outer cell. Silicon is there, which is having 4 valence electrons. So that means we can add this to this. Okay. So here you can see that. After addition, adding phosphorus to the pure silicon crystal result in a surplus electron and it becomes a free electron. This pure silicon at this moment, this can be considered as an insulator because there is no free electron present in the outer cell. Okay. When I add this phosphorus to the silicon, then this 4 electron will combine with this. They will make a bond, covalent bond with each other, but there is one extra electron present in the phosphorus that will acting as a free electron for conducting of electricity. So that is written and it becomes a free electron. So here you can see that pentavalent impurity is added to an intrinsic material. This is impurity. This is impurity. This is not a pure one. This is impurity which we are adding to the pure semiconducting material, pure silicon semiconductor. After addition, we get the extra electron which is free for electricity conduction. Such as silicon or germanium, only 4 of its valence electron lock into the covalent bond formation of atom structure. The 5th valence electron of an impurity atom is free and it can wander through the crystal. It can wander here and there through the crystal. So when we are applying some voltage to this particular P type of semiconductor, N type of semiconductor, then this free electron can move anywhere in the crystal and the movement of this free electron is nothing but the conduction of electricity. I hope you guys are getting what I am trying to say. So here silicon around 8 silicon silicon atoms are shown over here, and there is one phosphorus atom is there. Whatever the electrons are there, 4 electrons from this will form the covalent bond, with the electrons from the phosphorus, but still one will remain as a free, and that can wander or that can move anywhere in that particular semiconducting material crystal. That means atom. So as far as material is concerned, on a large scale or on a macro scale, number of impurity atoms will be more, number of electrons, free electrons will be more, and your conduction of electricity will happen. So this is only shown for one single impurity atom, but we are not adding only one single impurity atom, we are adding multiple atoms, so that we can have this multiple number of electrons for the conduction of electricity. I hope it is better understood. Then the next one is P type of semiconductor. Here electron is free. Okay, that's why it is called as N type. And in P type semiconducting materials, there will be a hole. So in P type, you can see that. Now in N type, we are adding pentavalent impurity. In N type, we are adding pentavalent impurity, 5 electrons in the outer cell. In P type, we are adding trivalent impurity, that means 3 electrons in the outer cell. So again the silicon is there. Aluminum, now here aluminum is taken as a impurity material. Aluminum is having only 3 free electrons in the outer cell. Okay, but silicon is having 4 electrons in the outer cell. So there is one hole, there is one electron missing in the impurity. So this pair, electron hole pair, is going to be generated in this particular semiconductor. This is, I am talking on the atomic level. As far as total material is concerned, there might be thousands of such kind of atoms present in that, or crystals present in that particular material, and that's why conduction of electricity is possible. This is only one representative image shown over here, but you have to imagine on the larger scale, macro scale, you have to imagine on a material scale, so that you will understand. When trivalent impurity is added to the intrinsic material, the 2 electrons get locked into the crystal structure. Impurity has 3 valence electrons. There is a hole in the covalent bond structure created by the lack of electron. Hole represents the incomplete covalent bond and exhibits positive charge. And in order to complete the bond and form a stable 8 electron structure, this is again print typing mistake, form chahiye yahan pe. So in order to complete the bond and form a stable 8 electron structure, a valence electron from nearby atom gains sufficient energy to break or to lose from its bond and then jump into that hole due to its attraction. ये image में थोड़ा overlap हुआ है, इसकी वजह से यहाँ पे break हो रहा है, ठीक है? But you have to understand. So what they are saying, I want to make it 8 electron stable compound over here. So for that 8 electron stable compound or structure, a valence electron from nearby atom, that means this valence electron from the silicon, gains sufficient energy, that means it has to have the sufficient energy rather to break this covalent bond or lose this covalent bond or it will get free from the silicon atom, so that it will form the pair. What is written over here? It has nearby atom gains sufficient energy to break loose from its bond and jump into the hole due to the force of attraction or due to its attraction, because opposite charge will have attraction. This is positive, this is negative, they will have attraction. So that we have to only provide sufficient energy. That's why temperature we have to increase. Silicon, we know that it is at 0 Kelvin, it is insulator. So इसको ये इलेक्ट्रॉन को यहाँ से ऊपर उठने के लिए और इसके पास जाने के लिए हमें कुछ तो एनर्जी देनी पड़ेगी. That's why we are heating it up. So due to the heat, vibration will increase. This electron may lose the bonding between this main atom, and it will get jump into the hole, forming the electron hole pair. Okay. So that is written in this particular sentence, that to form a 8 stable electron structure, 8 electron stable structure, valence electron from the nearby means from the silicon. अभी यहाँ पे देखो 1 2 3 यहाँ पे इलेक्ट्रॉन नहीं है, यहाँ पे कोई भी ले लो आप, यहाँ पे सिलिकॉन 4 4, यहाँ पे silicon 4, this 1, 2, 3, but 1 is not remaining. So to form 8 stable electron structure, valence electron from the adjacent element, that is silicon, this valence electron will gain some energy. It will lose the covalent bond, or it will break the covalent bond and jump into the hole to form the proper 8 stable electronic structure. Okay, and this jumping of the electron is going to be again responsible for conduction of electricity. Therefore, this type of impurity is called as acceptor. This impurity, as it is having three electrons, one is hole, so one electron is going to be accepted from the adjacent element. That's why it is called as acceptor impurity. In the pentavalent, there is one electron extra in the outer cell. That's why it may donate that particular, it is able to donate that particular electron for the conduction of electricity. That impurity is called as donor impurity. So don't be confused in this as well. Pentavalent impurity is always a donor. Trivalent impurity is always acceptor. Electrons available to fill the hole and complete the bond have been released by the nearby atom, whose bond have been broken and the hole is going to be created. Thus, the process will continue creating the mobility of the holes. Impurity atom provides the fifth electron becomes negatively ionized as accepts an electron. Germanium or silicon atom which releases the electron become positively ionized, and the net charge of the material is going to be still neutral, because यहाँ पे ये negative है but this is positive coming into the picture, so they will neutralize each other. Okay, so net charge in that particular semiconducting material may be a neutral charge. Any doubt? Any doubt in this P-type? We may have a question, explain N-type of semiconductors with suitable example and diagram. Explain P-type of semiconductor with suitable example and diagram. I think sufficient questions are there for the assignments. Assignment number 5, so you can start writing the assignment number 5, and the submission date for the assignment number 5 is next Wednesday. Till that time I will share the PPTs, or you have other ways to write the answers for that question. Okay. If you see the applications of these semiconducting materials, they are used as a temperature sensors. They can be used in 3D printing machines as well, semiconducting materials. They can be also used in microchips and self-driving cars. Nowadays in US, I think there are cars where there are driverless cars are there. There is no driver. You have to sit in that car and just give the program or give the command to the car. The car will take you to the destiny. If your luck is good. Okay, so in that case, how these are working? Basically, this is electronic magic, electronic and mechanical magic, and that's why robotics is coming in. Used in calculators, solar plates, computers, and other electronic devices. Transistors and MOSFETs, which are used as a switch in electrical circuits, they are also manufactured from the semiconductors. Microprocessors used for controlling the operation of space vehicles, trains, robots, etc. is made up of transistors and other controlling devices which are manufactured by using semiconducting materials. That's why Government of India has invested too much money in generating this particular semiconducting or semiconductor material industry. Now, how many of you knows hysteresis loop? Do you know the concept? This is not new for you. This is actually not new for you. This is called as hysteresis loop. This is coming again in magnetic materials. This is the property of the magnetic materials actually. So here it is, diagram is shown over here. This particular diagram is called as hysteresis loop. This particular diagram is called as hysteresis loop. Here you can see that magnetizing force is H in positive direction, magnetizing force in negative direction, and what are the resistivity, the flux density in positive and flux density in negative direction, and at the same time you can have this retentivity, coercivity. These are the properties. Again, then saturation in opposite direction, saturation in positive direction, flux density in opposite direction. Now what happens actually in this? When we are applying the magnetic field to the magnetic material, whatever the magnetization is going to be generated, it is lagging behind. So that is what written here. Hysteresis is the lagging of magnetization of a ferromagnetic material behind the magnetizing force H. So if we consider this H as a magnetizing force, if I start from origin of this particular diagram, I have applied this much of magnetizing force. When I apply the magnetizing force, my magnetic field should generate at this force only, but it is generating behind. That's what lagging. And when I increase this one, I can say that this is following the path and it will reach to the saturation of magnetic field at point A. And at the same time, you can see that this dotted line here, the specimen is assumed to unmagnified and the current is starting from 0 in the center of the graph. As H increases positively, B follows the red dotted curve from the origin to the saturation point A indicated by B max. So whatever the current has to follow or has to flow into that particular material, it is starting from the origin and reaching to this particular point. Everywhere you will find that this magnetic current, which is generated due to the application of magnetic field, this indicated whatever the B max. So this is lagging behind the applied magnetizing force. So hysteresis is nothing but lagging of the magnetization. I think this is not there in your syllabus, but just to get understanding of what is hysteresis look, or for revision purpose, I have purposely added this particular slides. So whatever the magnetizing force is H, and due to application of the magnetizing force, we will get the magnetic field produced in the material. So you can see that it is when we are applying the magnetizing force, the magnetic field will start from this one. So this much lagging is there as far as this definition is concerned. So specimen is assumed to be unmagnified. That means specimen is not magnetized initially. The current is starting from 0 in the center of the graph. From here current is starting. As H increases, B follows the red dotted part or this dotted line. As H increases, that means as magnetizing force increases, B, that is magnetic field, is following this particular path. And it will follow up to this particular point A. When I demagnetize the material, that means I am applying the force in negative, magnetic force is going to be applied in negative direction. In that case, it will follow the path like A to B. That means again, this much of flux density is going to be present in the material. So this much flux density is called as retentivity. That means that this material has retained the magnetic field after this much of magnetic flux has been retained of this value. So that is discussed in the next figure. You can see that as H decreases to 0, the flux follows the curve AB. And drops to BR, that is called as retentivity. That means whatever the magnetic flux is there, that is BR, and this much it has to come to 0, When initially I am going from here to here, that's why it is increasing and it is increasing like that. But when I am coming back to the original position on the same way, then it has to follow this particular path only, isn't it? But it is not following that path, it is following this path, and when my magnetizing force comes to the 0, my magnetic flux is again still there inside the material, showing this much value. So this much retained magnetic flux in the material is called as the retentivity of that particular material. Or it is also called as residual induction. This point represents the amount of flux remaining in the core after the magnetizing force is removed. After the मैग्नेटाइजिंग फोर्स, मतलब यहाँ से यहाँ आ रहा हूँ, मतलब मैग्नेटाइजिंग फोर्स मैंने निकाल दिया पूरा, तो ये निकालने के बाद मेरा फ्लक्स भी इधर आना चाहिए, क्योंकि फ्लक्स जनरेट किसकी वजह से हो रहा है, H की वजह से हो रहा है. बट H जब जीरो है तब ये भी B max भी जीरो होना चाहिए, बट वो नहीं हो रहा है. क्योंकि वो नहीं हो रहा है, मतलब सब रेसिडुअल, जैसे हमने रिटेन ऑस्टेनाइट की बात की थी स्टील केस में, वैसे यहाँ पे रिटेन फ्लक्स वी कैन कॉल इट एज, एंड दैट इज कॉल्ड एज रिटेंटिविटी. When H starts in negative direction, now what happens when H is increasing in the negative direction? Again this path will follow B to C. Again you can see that the core will lose its magnetism as shown by the following the curve from point B to C. जब मैं negative direction में मेरा force बढ़ा रहा हूँ, तब मुझे जो रेसिडुअल इंडक्शन यहाँ पे था या फ्लक्स था, वो क्या हो रहा है, जब मैं नेगेटिव डायरेक्शन, मतलब अगर मुझे मटेरियल को पूरी तरह से नॉन मैग्नेटाइज करना है तो मुझे मैग्नेटिक फोर्स नेगेटिव डायरेक्शन में बढ़ाना पड़ेगा, तब जाके मेरा ये जो फोर्स है, सॉरी फ्लक्स है और इंडक्शन जो है जनरेट हुआ वो जीरो तक आएगा. बट आई नीड टू reduce the magnetizing force in negative direction to get this zero value. Okay, that is written out in this one. The amount of magnetizing force required to completely demagnetize the core is called as coercive force, and it is designated by minus Hc in the figure. So this is minus. So this amount of magnetizing force which is required in negative direction to make the material non-magnetic, this particular force is called as coercive force, and that is shown by Hc over here. Again, as the peak of the negative cycle is approached, the flux follows the portion of the curve labeled CD. Again, it will follow this curve labeled CD. Point minus Bmax represent the saturation in the opposite direction from Bmax. So from point D, the negative value of H decreases to point E. पॉइंट डी से यहाँ पे जाएगा और फिर यहाँ से सैचुरेशन के लिए यहाँ तक आएगा. मतलब हमें क्या लग रहा था कि यहाँ से यहाँ जाएगा, बट नहीं, दैट इज नॉट द केस. इट विल मूव फ्रॉम हियर टू हियर एंड देन कम टू दिस पर्टिकुलर पॉइंट. फ्रॉम पॉइंट डी माइनस एच वैल्यू डिक्रीजेस टू पॉइंट ई विच corresponds to the zero magnetizing force. Again the flux minus Br still remains in the core. तो जब मैं यहाँ से यहाँ जा रहा हूँ तो मेरा फ्लक्स अगेन माइनस Br, this is again remaining in the core. Okay, so this is something about the hysteresis. Look again, one more thing about this one. Coercive force plus Hc. Coercive force plus Hc is required to reduce the core magnetization to zero. That means if I want to make the material zero magnetized, I need this much of magnetizing force. As the magnetic force continues to increase in the positive direction, the portion of the loop from point F to A, is completed, and the periodic reversal of magnetizing force causes the core flux to repeatedly trace out the hysteresis. Look, so I have taken this from this particular link. You can go to that particular link. Take it out in the semiconducting materials. We have just discussed what is semiconducting materials, what are their general properties. Then we have seen the types of semiconducting materials, that is intrinsic materials which are pure semiconductors, extrinsic materials which are impure semiconductors. Extrinsics are again classified into two types, p-type and n-type. In p-type there is a pentavalent impurity is added to the semiconducting material. In n-type, in p-type, trivalent impurity is going to be added. P for positive charge, you can remember like this. P for positive charge, a hole is a positive charge. So when hole is going to be created, when there is trivalent impurity. And n-type means negatively charged semiconductor. So n is electron, that means there should be a free electrons for the conduction of electricity. So that is n-type semiconductor we have seen, and in that case we use pentavalent impurity for making that semiconductor materials. After that we have seen p-type and n-type, how doping or how mixing of impurity with the pure semiconducting material is going to be done, that we have discussed. We have discussed something about the n-type with suitable example. We have discussed something about p-type with suitable example, and after that we have seen some specific applications of the semiconducting materials. Huge applications like temperature sensors, 3D printing machines, microchips and cell drivers, calculators, solar plates, computers, electronic devices, transistors, MOSFETs, and microprocessors which are used in robots, which are used in vehicles, in trains, as they can be used as a controlling devices in every field. And after that we have just discussed something about the hysteresis law, how it is going to be formed. And after that, this will start in the next session. Thank you very much.